So here we are at the Landscape tab. On this tab, we enter data for the reservoir catchment. Very briefly, a catchment, also called a watershed, is an area of land that drains precipitation to a specific stream or river, and in our case, a reservoir. A few important things to note. First, for the GRES model to calculate emissions, you must enter input values into every gray cell. So these gray cells here, you must enter data there. Data can be entered into the white cells here if you have that data, and this will provide more accurate results, but they're not required to run the model. The blue cells here are going to be calculated by GRES. Next, if you hover your cursor over the cell, or over a cell, you'll get a little box that describes the input, and this text comes straight from the GRES user guide. You can see that again, so this is population within the catchment area, upstream of the dam, and numbers of persons. Again, that comes from the user guide, not to be confused with user guidelines here on the right-hand side. So do pay attention to the user guidelines as well. You'll see that this tab is separated into three sections. One for catchment data like area, population. Then we have post-impoundment land cover in the catchment, so land cover in the catchment area. And then we have pre-impoundment land cover in the reservoir area. Really quickly, the pre-impoundment land cover in the reservoir area. This is going to be an estimate of land cover in the area that was inundated by the reservoir. So before the reservoir was there, what was the land cover like? And that most likely was some type of river valley. So what was going on there before they flooded it? This tab is also really where the Google Earth Engine comes in handy, because a lot of these values on this page can be hard to find if you don't know how to estimate them on your own in GIS software. So Google Earth Engine can handle a lot of that. You can get land cover, and we'll estimate pre-impoundment land cover as well. Okay, so like I mentioned, I'm going to use the Harris Reservoir down in Alabama. We're going to use data from that analysis that we've previously done. So we're going to import our saved parameters, go to Browse, and then go and find your .mer file. You can see I have a couple of them. So here's Harris. We import it. And now you can see that it brings in all the data that we've previously saved. So catchment area, population, all these values. Over here in the top right are our current totals. This is in tons of carbon dioxide equivalent per year. So we've got our post-impoundment emissions, again, tons of carbon dioxide equivalent per year. We have our pre-impoundment emissions. We've got a negative value here. If we had unrelated anthropogenic sources, we would have values there. So a note about this negative number. This is basically saying that before the creation of this reservoir, that area underneath what is now impounded and inundated with water was a carbon sink, or CO2 sink. You can see it's a very forested area before impoundment. A lot of grass cover as well, so that's likely what led to this pre-impoundment sink of emissions. Alright, let's move on to the Reservoir tab. On this tab, we're going to enter data related to the reservoir itself. Again, gray cells are required, white cells are not, but do enter them if you have them. Enter those values if you have them. This tab is a bit different from the last though. GRES will actually calculate values for the blue cells. You can see those blue cells here. But if you have an actual value to enter, then enter that and it will override the GRES estimation. So let's look here, for example, thermocline depth. We used documents related to the relicensing of Harris Dam. They were publicly available. In those relicensing documents, it listed the thermocline depth was 10 meters. So we entered that here. But you can see, if we didn't have that value, GRES would give us an estimate. So we have these clockwise buttons here. So you click on these clockwise arrows, it'll revert back to the GRES estimate. And in this instance, GRES estimated the thermocline depth to be 1 meter. And you can see that that's actually changed our post-impoundment emissions in the top right. So let's go ahead and change this back to our known value of 10. It's a big difference. So enter that here. And if you'll notice again in the user guidelines, the first thing it says is project-specific information should be used when available. So use those data if you have them. So we've already preloaded all of our input data, but once you start entering data into the Reservoir Data tab, you'll start to see these post-impoundment emission rates up here in the top right being calculated. Those values will change as you fill in more and more of the cells. And as you enter values, you'll see how sensitive the GRES model is to certain values. As you change those values, they may have a big difference on these post-impoundment emission rates. So let's look here. We have a thermocline depth of 10 meters. We have a water intake depth of 8.8 meters. So this water intake depth is just above our thermocline. And this is actually important. So at this point, water is being pulled from above the thermocline, but if we change that, if we change the depth of the water intake to be below the thermocline, let's say it's 12 meters, 2 meters below the thermocline, you can see that again, that changes our post-impoundment emissions. So what's happening here is with this deeper water intake depth, water is being pulled from this kind of methane-rich, low-oxygen environment below the thermocline. It's running through the turbines, and it's kind of being degassed and released into the atmosphere. So one way to determine which values are most important at your reservoir is to undertake a sensitivity analysis. There are different approaches to this type of analysis, but one that we used was simple, and that was to change these values by positive and negative 10%. And we can see how this affects your post-impoundment emission rates. So up until this point, we've been very objective and have quantified various catchment and reservoir characteristics. But now we're going to get more subjective and more qualitative. Because a reservoir can provide many services, GRES asks us to allocate the proportion of emissions to each service. To do that, the user will need to determine the primary, secondary, and tertiary purposes of the reservoir. So how do you determine the importance of each service? Well, GRES allows you to choose 3 different methods to determine the importance of services: the explicit prioritization method, the operating rule curve method, or you can describe in detail how you've determined allocations. The GRES user manual notes that there is no current consensus on the best approach, and the tool currently bases allocation on the importance of the service on the operating regime of the reservoir. The explicit prioritization method ranks services in terms of operational hierarchy, and this method of prioritization is currently in place in India, Pakistan, and Turkey. But for our analysis of the Harris Reservoir here in Alabama, we use the operating rule curve method. You can see the definition of primary, secondary, and tertiary under both of these methods in the table here at the bottom of the page. To determine the importance of these services under the operating rule curve method, we used appendices found in the U.S. Army Corps of Engineers Water Control Manual, the Alabama Coosa-Tallapoosa Basin. That document has the operating rule curve for different hydropower projects, and we're able to determine the importance of these services from that document. So let's again take a look at Harris Reservoir, where our primary service is hydroelectricity. So primary services will be allocated 80% of emissions, secondary services will receive 15% of emissions, and tertiary services will receive 5% of emissions. Services that don't exist at a reservoir are marked as NA, you can see that here, and there can only be 3 services for each level of importance. Emissions are evenly allocated amongst those services. So you can see here for our tertiary services, we've got 3 tertiary services. We can't have any more, and that 5% is split evenly amongst those services. There are also 2 cells over here on the right of the page where we enter installed capacity at the dam and the total annual generation of electricity. We found installed capacity on the dam operator's website. We found total annual generation in a report to FERC, the Federal Energy Regulatory Commission in the United States. Dam operators are required to report a lot of this information on an annual basis, so these data aren't too hard to find. So all of this is really important because it allows us to calculate the emissions intensity of our hydropower project. The emission intensity is simply the amount of greenhouse gas produced per unit of electricity generated, and this number is often used when determining whether a reservoir meets a predetermined threshold of clean energy. And for a lot of people doing this analysis, emissions intensity may be one of the most important outputs from this model. Alright, now let's hop over to the construction tab that's going to be located here at the far end of these tabs. So this tab is where we'll enter any data we have related to construction. Important to note that this isn't required for the model to run, but it will give you more accurate assessment of the reservoir's footprint. The first thing to point out is that we have these three sections. We have own assessment, we have basic assessment, and more detailed assessment. If you enter data into the basic assessment cells, do not enter data in the more detailed assessment cells or in the own assessment cell. If you enter data into one or more, into more than one of these sections, the tool will basically double count those values, and it'll inflate your emission rates. Own assessment, as it says here, if you've undertaken your own assessment of emissions at a project related to construction, you would enter that value here. For the basic assessment, we have earth and rock fill, concrete and steel. So we'll enter these values here. So this is the amount of earth moved, concrete moved, the amount of steel used in construction. If you know the distance those materials are moved, you can fill in these cells here. Down in the more detailed assessment, again, it's exactly what it says. It's a more detailed assessment. It asks for more data. There's more room for more data, basically. Now, if you're doing an analysis of an existing dam in the United States, it's likely going to be pretty tough to track down the level of detail needed for this more detailed assessment. And it's probably going to be pretty tough to even track down the questions asked in the basic assessment here. When we completed our assessment of Harris Reservoir, we were able to find some of these numbers in magazines published by the construction industry. We found some in a magazine published by the dam operator or the reservoir operator for homeowners along the lake that they created there. And ultimately, things like rock and concrete moved commonly aren't really going to end up in public documents related to dam relicensing, many decades later. All right, now before we get to our results tabs, let's look at the emission factors tab and the earth engine tab. So again, we mentioned this in the introduction. We recommend not changing the emission factors here and sticking with the default. The default factors used by GRES are going to be consistent with the emissions factors used by the IPCC. If you want more information, check out the GRES technical document for more information. Over here on the Earth Engine tab is where you'll acquire missing data using Google Earth Engine software. The use of Earth Engine is really outside the scope of this video, but you can click here to download a very well-written user guide provided by the GRES team. They provide you with all the code you need to run Earth Engine and acquire things like watershed land cover and certain reservoir characteristics. To use Earth Engine, we do recommend importing a vector file for your watershed. If you don't have the capability to delineate a watershed using GIS software, the easiest method is to use the United States Geological Survey StreamStats software. This software is easy to use. It's a web-based tool that will delineate a watershed simply by selecting your stream outlet point on a map, just clicking on that outlet point. Now, for a reservoir, that outlet point would be the most downstream dam of that reservoir. StreamStats will provide you with a vector file that you can download and then import into Google Earth Engine by following the directions in the user guide.